I've talked previously about how you do basic math using matrices. Right now, I'd like to talk about matrix inverses and the idea of a determinant. And to motivate that, I'm going to set up a system of equations, ordinary system of equations I want to solve. Here it is, 2x minus y equals negative 1, and 3x plus 2y equals 9. I want to solve for x and y. Now, there are lots of ways of doing that. I could eliminate variables and things, but I want to think of this as a matrix equation because it turns out that way of thinking about systems of equations is really powerful, generalizes, it leads us to lots of good places. So how would I write this as a matrix equation? Well, let's look. If I write it as a square matrix of the coefficients times the column vector xy, and set that equal to a column vector of the two right-hand sides, what that does, if I multiply it out, you can try our usual matrix multiplication thing. The first row times the first column, 2x minus y is our top element, and 3x plus 2y is our bottom element, equals minus 1, 9. It gives us exactly the system of equations again. The two equations end up being the two rows of the matrix on each side, and we set them equal. So this is the way we're going to set this up, and algebraically I'm going to write this as matrix M, my 2 by 2 matrix up front, times capital X, this column vector of the unknowns, equals capital B, a column vector of the results on the right-hand side. This is just a symbolic way of writing this equation. So if these were ordinary numbers instead of matrices, what would I do? Well, it's pretty obvious. First, I would double check that M isn't 0. So if M isn't equal to 0 for ordinary numbers, I would divide both sides by m. I would get 1 over m times mx equals 1 over m times b. And 1 over m times m is just 1, right? Those would cancel out, and I would just get x. 1 times x is x. So that's how I would solve for numbers rather than for matrices. So I want to understand how to do this same thing for matrices. To be able to do this, to solve this in matrix form, I want to be able to do exactly these sorts of steps to do it. And you're going to find that we need to mix things up a little bit. We can't do it in exactly the same way we would numbers, but a lot of it's going to be close. So where do I start with that? Well, one place to start is with the idea of a matrix inverse. I should close this off. So a matrix inverse, we want something, an inverse of anything, right? 1 over m over here is a number. We want something like that. We want to say m inverse, m to the minus 1 power is the way we'll write the inverse. M inverse times m should equal the identity matrix. This only works for square matrices. So n by n matrices. It only works for n by n matrices, and this is the n by n identity matrix. This sort of goes without saying. But if this is n by n, then that will be n by n. The product is n by n, and we get the identity. So we want a product of two matrices that gives us the identity. And just to be clear, that should also be what we get if we do it in the other order. Because remember that order matters in matrix multiplication. For an inverse to be well defined, we want to work on both sides. That's usually not going to be a problem. Okay, so this is the idea of a matrix inverse. And, well, how do we do this? How do we find this? For some matrices, it's really easy. So, for example, if I had the matrix 3, 0, 0, 0, 5, 0, 0, 0, well, make it negative 5 just to make it interesting, and I want to find the inverse of that matrix, all I need to do, you can check that this is true, is 1/3, 0, 0, 0, minus 1/5, 0, with the minus 0, 0, 1, 1 over 1. That's what that inverse will be. And you can double check this works, right? The first row and first column would be 3 times a third is 1 plus 0 plus 0. First row, second column would be 0 times 0, 0 plus 0 plus 0, 0 plus 0 plus 0, 0 plus 0 plus 0, 0 plus negative 5 times negative 1/5 is 1, 0. So you'll get the identity matrix, 1, 1, 1 down the diagonal when you multiply. This is obvious for a matrix that is diagonal like this. The inverse is easy to see. But what about this matrix? 3, 0, 0, 0, 0, 0, 0, 0, 1 inverse equals, well, what would I have to write? You can see what I have to do. I have to do 1/3, 0, 0, 0, 1 over 0, 0, 0, 0, 1. Uh-oh. This right here is a problem. This is a matrix that has no inverse. Just like 1 over 0 would be undefined, which is why we checked that m wasn't equal to 0 over here, there's no inverse of this matrix. It's ill-defined. So some matrices have no inverse. And those matrices are called singular, which for us, singular matrices are, you can think of in this context as being bad matrices. They're the naughty matrices that don't have inverses. So if it's a singular matrix, it doesn't have an inverse. Matrices that do have inverses are called non-singular. Non-singular matrices do. So that's the idea of what a singular matrix is versus a non-singular matrix. So non-singular means not bad. It means it's good in this context. It works. Okay, so how do we figure this out? How do we determine whether a matrix has an inverse or not? What lets us determine that? It turns out the way you determine it is with something called the determinant. So the determinant of a matrix, if I have a name for some matrix to use to give a determinant, if I had a matrix, call it A, if A equals 4, 3, 1, minus 2 or something, then the determinant of A, the determinant det A, determinant of A, can be written as the magnitude, it's absolute value bar sort of around it, 4, 3, 1, minus 2. So you replace the usual parentheses or brackets around your matrix with vertical bars. That means take the determinant. That's what it's going to tell you. And there's a very simple definition of this. To find this determinant of A, we just take the diagonal, we multiply those. So this is 4 times minus 2 minus the anti-diagonal here, minus 3 times 1. Or in other words, minus 8 minus 3 gives me minus 11 for this case. The general formula for the determinant of a 2 by 2 matrix is, if this is the determinant of A, B, C, D, where those are just numbers, right, a 2 by 2 matrix, that determinant is AD minus BC. That's what it is. That's just the definition of the determinant of a 2 by 2 matrix. There's a complicated sort of recursive definition of the determinant of a 3 by 3 matrix in terms of the determinant of a 2 by 2, and n by n in terms of a bunch of determinants of n minus 1 by n minus 1. It's ugly. You don't want to deal with this. If you want to take the determinant of a larger matrix, use a computer or something. That said, for 3 by 3, there is a trick you can use that's pretty quick. If I have A, B, C, D, E, F, G, H, I as some 3 by 3 matrix, arbitrary 3 by 3 matrix, there's this trick you can use to find its determinant without having to do a whole big ugly calculation. Well, it's a little ugly, but it's much better than the recursive thing. What you do, you go down the diagonals. You say A times E times I. And then you add the next diagonal. B times F times, we wrap around, times G. So plus B times F times G. And then you do the next diagonal. C, you wrap around, times D times H. Plus C, D, H. That's a bunch of adding. And now we have to subtract the anti-diagonals, whatever you want to call them, the opposite diagonals. So minus C times E times G. And then minus, what do we have? How about B times D times I? B, D, I. Do I have another color to do? Not really. Oh, sure. Minus the last diagonal, A, wrap around, times F times H. There's A, F, H. There you go. That's the equation for the determinant of a 3 by 3 matrix. I've never had to calculate by hand beyond this, except maybe like once in a class years ago. You just use a computer if you need a larger determinant, because otherwise it's a royal pain to do. So there you go. That's the determinant of a matrix. Why is this important? Well, what's the determinant of this matrix? 3 times minus 5 times 1 and the rest of it's going to be 0. They're going to be zeros multiplying everything else. So this determinant's minus 15. This determinant, this matrix determinant is 3 times 0 times 1, and everything else will be multiplied by zeros. This is just 0. If the determinant of a matrix equals 0, I guess I would say it is singular. It has no inverse. It is singular. There's no A inverse. That's the key idea, that the determinant determines whether or not our matrix is singular. If the determinant is 0, it's singular. So, okay, we can work with that. We can come over here. Let me get rid of this little note down here. I guess I should have kept that. Oh well. So I talked about this. How does this tell us how to find the inverse, though? And the answer is it really doesn't. There is, when I said there's an ugly formula for determinants of 3 by 3 matrices, there's an even uglier formula for inverses of 3 by 3 matrices. It's an ugly recursive formula again, I think. But what we can do, for at least, again, use a computer if you need to make matrix inverse in most cases. But for the 2 by 2 case, what do I would say? For 2 by 2 matrices, for a matrix A, B, C, D, this is our general 2 by 2 matrix, any 4 variables A, B, C, D. If this is A equals this, then A inverse is, here's the formula we're going to use, 1 over the determinant of A, that's written badly, 1 over the determinant of A times, and there's this weird thing, D minus B minus C A. There's a formula that tells you what to do here, tells you what to do for larger ones. Again, just use a computer or just use this formula. So for us, let's look at, this is the general formula. So let's look at our matrix over here, the one we want that's in our inspiration for all this. For our matrix, our M inverse is going to, well, I shouldn't start with M inverse, I should start with the determinant of M, right? And can we even solve this system of equations? The determinant of our M is going to be, let's see, it's 2 times 2 minus 1 times 3, which is 4 minus a negative plus 3, which is 7. So our determinant is 7. That means it is non-singular. That means it will have an inverse, and we can use this formula. So that means that our M inverse is going to be 1/7 times, let's see, 2, 1, minus 3, 2. Okay, or I guess I can write this as 2/7, 1/7, minus 3/7, 2/7. That's what I come up with for my M inverse. Again, 2 by 2, we can do this easily. Larger ones will be messed. But we can try this. Let's just test it out to make sure this works before I do a bunch of work solving things. Just to see how this plays out, let me do 2 minus 1, 3, 2 times 2/7, 1/7, minus 3/7, 2/7. If I do that, let me go through the 4 components. You can try this at home. Maybe I'll pause. You can pause the video. Try it yourself. Okay, let's try it. 2 times 2 is 4/7 minus negative 3, 5, 6, 7/7 up here. 7/7. This is 2 times 1/7 is 2/7 minus 2/7, that's 0. This is 3 times 2/7 is 6/7. 6/7 plus 2 times minus 3 is minus 6/7, so that comes out to be 0. And over here, 3 times 1 is 3/7, 2 times 2 is 4/7, 3 plus 4 is 7/7, which is, in fact, the identity matrix. Yay, it worked. So these are, I could check the other way too, but it would be boring for you. These are inverses. We have the correct inverse. So what's that tell me? At this point, I can take my original equation here, my mx equals b equation, and I can multiply both sides of the equation by the same thing from the same side. I'm left multiplying both sides by m inverse. Right? I'm left multiplying both sides by m inverse. that means that these two terms, m inverse by m, I know that is equal to the identity matrix. So then I have identity times x. That tells me then the identity times anything is the same matrix. It doesn't change it. So this just tells me that x equals m inverse b. And I can work that out, right? I'm juggling my pen cap here. Let me work out what that comes out to. What answer I get from it. Let's try it. When I work that out, I'm going to find my x is little x, little y. That's my x vector, my vector of unknowns. X equals m inverse, we have here, is 2/7, 1/7, minus 3/7, 2/7, times my b over there was minus 1, 9. What's this come out to be? Let's see. This is, I'll just write it all out. There are going to be 2 rows and 1 column. So minus 2/7 plus 9/7. Is that right? Did I have that right? Oh, I feel like I saw something different the last time I did this. Hang on. Well, minus 2/7 plus 9/7. Yeah, that's right. Plus 9/7 is my top one. And this is right, yeah. And minus 3 times minus 1 is plus 3/7. 2 times 9 is 18/7. 18 plus 3 is 21. So this is going to be 3/7 plus 18/7. Or in other words, this is 7/7 and 21/7, or 1 and 3. So I get that x equals 1 and y equals 3. And if you check that out, 2 times 1 is 2, minus 3 is negative 1. 3 times 1 is 3, plus 6 is 9. It works just right, and this method works. Now obviously this is a kind of roundabout way of solving a simple system of equations like this, but it turns out that computers are very good at finding matrix inverses. If you took a full linear algebra class, you'd learn much more efficient ways than doing this determinant and weird recursive thing I talked about. There are more efficient ways of finding an inverse, and you can use those, a computer can use those, to solve matrix calculations really efficiently. And that's where this becomes really powerful. The math we use here, using matrix inverses and things, will come up all over the place as well. So I hope this gives you an idea of what the equivalent of division is for matrices and how you can make it work. You find the determinant to make sure you can find the inverse, then you find the inverse using a computer or using this formula for 2 by 2 or whatever, and then you can just use that inverse to left multiply. I guess if your m was on the right, you would right multiply, but to put your m inverse next to your m so that it gives you an identity and you can solve your equations. It's pretty cool, and I like the way it works.